today, but once we go through a couple of iterations, it will become clear. Alright, so again, let us consider a directed graph. It could be an undirected graph also. And the edge weights could be positive or negative. So any combination of edge weights is okay. So what we are going to really do is going to find is the shortest path between any two vertices. So that's why we are going to have a two-dimensional matrix V1, V2, V3, V4 for the vertices. So as I said, we are going to use two matrices. One is the distance matrix to keep track of the shortest path distances from one vertex to another vertex. And the other is the predecessor matrix to keep track of the predecessors for the shortest paths. Now to begin with, all we have is the edge weight matrix. So that itself is the initial distance matrix. So if you look at this given graph, you have again, we do not have any self loop from a vertex to itself, so the diagonal is going to be 0 to begin with at least. Now if the graph has negative edge weights, you can even reduce the shortest path weight from a vertex to itself to something less than 0. You may encounter that. So as we go through the iterations, we may say the shortest path weight from V1 to V1 is negative 10 by going through some intermediate vertex. That's possible. But will not have any self loop in the graphs that are given to you. So to begin with, from a vertex to itself, the weight is 0. So all the entries in the diagonal is 0. Now we'll follow the convention of storing the outgoing edge weights. So from 1 to 3, the weight is 3. So that means the estimated path weight that we initially know from 1 to 3 is 3. On the other hand, there's no edge from 3 to 1. So from 3 to 1, we have to look at this row 3, column 1. The estimated path weight is infinity because we don't know currently a path from vertex 3 to vertex 1. Now, so that is why for vertex 1, we don't have an edge to 2. So the estimated path weight from vertex 1 to 2 is infinity. Similarly, there's no edge from 1 to 4, so the estimated path weight from 1 to 4 is also infinity. So you currently just have an edge to 3, vertex 3 and of weight 3. Now similarly for vertex 2, you currently have an edge only to 1, so and the edge weight is 2. Vertex 2 to itself is 0. Vertex 2 to 3, there's no edge from 2 to 3, so it is infinity. Now there's no edge from 2 to 4, so it is also infinity, and so on. Now how to fill the predecessor matrix? So if there's an edge from one vertex to another vertex, that starting vertex itself is a predecessor. So here we have an edge from V1 to V3. So V1 itself is the predecessor. So if you have an edge from U to V, U is the predecessor for V. So we have an edge from V2 to V1. So V2 is the predecessor. So you have to reach V2 to reach V1. That's what predecessor means. So V2 to V1, there's an edge. So V2 is the predecessor. Now V3 to V2, there's an edge. So V3 is the predecessor. V3 to V4, there's an edge. So V3 is the predecessor. Now V4 to V1, there's an edge. So V4 is the predecessor. So when that is why I said if you have an edge from U to V, U is the predecessor for V. So that row, that corresponding row ID itself is the predecessor to begin with. Okay, so V1 is the predecessor for any edge to any of those vertices. V2 is the predecessor to any of the vertices, and so on. Okay, so if you don't have an edge, so that means if the edge weight is infinity, the corresponding entry in the predecessor table is not applicable, means null. We don't know currently anything. So we can keep it null or not applicable. So that is how you initialize the distance matrix and the predecessor matrix. So you have a graph of 4 vertices. We have to go through 4 iterations. So let us do the first iteration. So when I say I am doing the first iteration, that means I am considering vertex 1. So again, remember, we are labeling the vertices 1, 2, 3, 4, V1, V2, V3, V4. So the iteration numbers correspond to the corresponding vertex that we are considering as a possible intermediate vertex. So in iteration 1, it means I am considering V1 as a possible intermediate vertex for a shortest path between any two vertices. So as I indicated in the general principle, we are going to highlight now the row 1 and column 1. So we can do that in the current matrix itself. We are highlighting the row 1 and column 1. So this is row 1 and column 1. and these are the other entries that we are going to fill in the sense we are going to see if we can reduce them from what we know currently. If we cannot reduce them what we know currently, we are going to use the same thing. Now how to reduce them, or how to see if we can reduce them, we are going to see if we can go through V1 and reduce the entries that we know for the distances. So let us do. So if I want to fill up this cell, let us pick something, say V2 to V3. We can fill up the cells in any order. We need not go through row wise. But let us. So that's why I'm just picking some general cell. Say V2 to V3. I'm trying to fill this cell. Currently, we think the path weight is infinity from V2 to V3. So what we are going to see is, can we reduce it further from infinity by going through V1? So if I going through V1, what we have to do? We have to see whether, so it is like this. So this is our entry V2, V3 and K is V1. So we have to compare, we have to add from I to K plus K to J. That means by going through from V2 to V1 and then from V1 to V3. Right, so you're trying to see if you're going through V1. So you're going to go from V2 to V1 and then from V1 to V3. So in that highlighted row and column for V1, so from V2 to V1, this is the value 2, and V1 to V3, this is the value 3. So 2 plus 3, is it less than infinity that we know currently from V2 to V3? The answer is yes. So we can put this as phi as the distance from V2 to V3, and we got that by going through V1. How can we enter that information? In the predecessor matrix, you see here for V1, that's a highlighted row, whatever is the predecessor from V1 to V3, because you see there's a path from V2 to V1 and then V1 to V3. So the later path V1 to V3, on that later path from V1 to V3, the predecessor is V1, and use the same predecessor here as a predecessor from V2 to V3. So like I indicated here, whatever is the predecessor from K to J, because looking at from I to K then K to J. So the path from K to J, whatever is the predecessor from K to J is the same as the predecessor from I to J. So that's why we are going to say whatever is the predecessor from V2 to V1 to V3, this V1, right? This is the same as the predecessor now from V2 to V3, because we go through V1 and this is now the predecessor from V1 to V3. We enter that same predecessor here. Okay, so that is how I fill the tables. Let us do 1 second. Let me check the time. Okay, we're almost out of time. Let me do a couple of entries here. So we say this phi and make this V1 as the predecessor. Now let us do this. So currently this entry is 0. So in order to see if we can reduce from 0 further down, we have to add the corresponding values. So always highlight. So from the cell, you can add a line, a horizontal line to the highlighted column and a vertical line to the highlighted row. Where they meet, those are the two cells you have to add. So in this case, if you add a horizontal line to the highlighted column, it is 2. If we add a vertical line to the highlighted row, it is infinity. So we are going to check 2 plus infinity, is it less than 0? No. So we stay with 0. So if you are not changing, enter the same predecessor information we have. So that is not applicable here. So enter the same not applicable here. So only when you are changing an entry, you have to update the predecessor. Like in this case. So if you want to decide which row, two cells you have to add from this cell. So this is I comma j. Draw a horizontal line to the highlighted column that meets here at value 2. Draw a vertical line to the highlighted row that meets here at 3. So we are going to add 2 plus 3, that is 5. That is less than the cell value here, which is infinity. So right here infinity. So since we changed the entry, the predecessor has to be from that row for V1, from the highlighted row. So we have to really highlight this row and make this corresponding V3, because we are looking at V2 to V3. So look at from V1 to V3, what's the predecessor? The predecessor is V1. So write V1 as the predecessor here. Okay. So in order for you to practice, I given the empty cells. So after you go through the iterations, these are the values you will come up with for the distance matrix and predecessor matrix. So I encourage you to practice this example. So we'll come back and do this example next time and go through one more example for Floyd Warshall algorithm. Okay. So with that, we'll stop for today.